In this video, you and I will take a look at how we can verify both the control and data plane in an MPLS Layer 3 VPN. Let's jump in. Here are the opt-out questions for this video. So take a moment, read these 4 questions, and if you are comfortable and know the answers to all of these questions, you can jump to the next video. Otherwise, let's begin. One of the challenges that we often face is walking into a customer network that we did not design or implement, yet they have some type of problem and they want us to troubleshoot it. What I've discovered is that it often helps to break things down into their individual components. For example, the control plane is responsible for allowing the routers to learn what to do. And I also have found that focusing on one specific route, for example, instead of looking at the entire routing table, take one specific route and follow it all the way through just to validate that the control plane is working for that network. And then if the control plane is correctly advertising that network, then I would look at the data plane from a customer perspective who's sending a packet and troubleshoot that data flow as well. So our control plane in an MPLS Layer 3 VPN application is quite complex. We have a lot of little moving parts. Inside our core network, we have IPv4, OSPF, and MPLS. We also have, between the provider edges, we've got multi-protocol BGP from R1 to R5 in our case. Also, R1 and R5 are running VRFs, and they're running a customer IGP in the case of Acme 1, CBT 1, and Acme 2. We're also running external BGP between R5 and CBT2. So if we were troubleshooting the control plane, maybe we pick one specific route. For example, we know Acme Site 2 has the network 192.168.111.2. That's a 32-bit route. And the process regarding the control plane and advertising that route would be sent via an IGP down to R5, so we're running RIP here. It would be received on the VRF for Acme. And so we just verify each of those steps. We could look at the VRF routing table and say, okay, did that route, yes or no, make it into the VRF. Our next step is to have R5 export that route out of the VRF, and as it does so into BGP, it has the route distinguisher, the route target, the VPN label, making it a VPN v4 route. So if that works, for example, we can take a look at the BGP tables and say, do you have a VPN v4 route in there? Then the next step would be to advertise that route to the other PE. So we could verify that as well on R1 simply by looking at the VPN v4 routes on R1. Do you, yes or no, have a route for 192.168.111.2? And if he doesn't, we might want to troubleshoot that BGP neighborship between R1 and R5. If R1 does have the VPN v4 route, its job, based on matching the route targets, is to import that route into the VRF on R1. And if that works successfully, we should be able to see in the VRF for Acme on R1, we should be able to see this network. And if we did our redistribution correctly, it should be advertised up to Acme Site 1, and it then should be in their routing table. So that's the control plane. Now to go a little bit deeper into this, I'd like to talk about the VPN label that R5 added to that route as it became a VPN v4 route. And let's say, for example, that the label that R5 added is 535. Again, in our lab, we assigned R5 to use a range between 500 and 599. So that's our little VPN label for that VPN route inside of BGP. Now what's going to happen is when R1 exports that route into the VRF, it's going to remember what R5's VPN label is for that network. And here's why R1's going to remember that. If we have somebody like Bob. And just for a moment, I'd like to talk about the data plane. If Bob is sending a packet out to 192.168.111.2, and that packet goes this direction, when it's received, R1 is going to know that R5's VPN label is 535 because that was part of the advertisements that R1 received. So check this out. When we start forwarding a packet to 192.168.111.2, R1 can include the label of 535, so that way when R5 receives it, it looks at the inbound label of 535 and says, boom, I know exactly what to do with this. So then R5 can forward the packet up to Acme at Site 2, and then it's up to Acme at Site 2 to route within his organization for that IP address that he's advertising. Also in our topology, one of the reasons that I set the label ranges for each of the routers is that so when we see, for example, a VPN label of 535, and we see it over here on R1, that R1 is remembering that VPN label associated with that network, we'll know absolutely who sourced that label. It was R5, and it has meaning for R5. So that's the control plane for the layer 3 routes. Between Acme Site 2 and Acme Site 1, it would also work the same in the other direction, as Acme Site 1 is advertising the 172.16 network space over here. It would follow the same exact process as it propagates from left to right. Next, let's you and I take a look at the data plane, the actual transit traffic that's going to be coursing through our network. And we're going to use a user like Bob. And I like putting a name on the item or the individual who's sourcing the traffic because it helps us visualize somebody actually sending traffic. So let's say Bob does a ping to 192.168.111.2. That packet from Bob is going to be routed internally in his network until it reaches this router, who, in his routing table, knows how to reach 192.168.111.2. He learned it via OSPF from R1 through the OSPF process that they share. So the transit packet gets forwarded down here. R1 receives it, and it looks at that packet. And when R1 sees the destination IP address that it's trying to get to 192.168.111.2, R1 knows a couple of things. Number one, it knows that the VPN label that R5 is using for that destination network is 535. So what R1 will do before it starts forwarding it over the label switch path, it will inject or impose label 535. Now that label, the VPN label, really doesn't have meaning to R2 or R3 or R4, but it does have meaning to R5. So what R1 cleverly does, it's going to impose this as the bottom label. Now what does that imply, the bottom label? Well, it implies that there's a top label. Because you see, when R1 learned about this network of 192.168.111.2, it learned that via Border Gateway Protocol, and it learned it from R5. And when R5 advertised that, the next hop to reach 192.168.111.2 is R5's IP address of 5.5.5.5. So the second label that it's going to add, which is also called the top label, or sometimes called the transit label, is the label that we're going to impose as the top label to send that packet across the label switching path, which is right there, the LSP. So I want to go back several videos with you and ask you a question about what label R1 is going to impose as the top label to get a packet over to 5.5.5.5. And if you're saying, Keith, I got this, it's going to use the local label that R2 is advertising for 5555. So regarding this LSP for 5.5.5.5, let's say that R2, regarding that destination, chose the label of 209 for 5555. That's the goal. That's the destination we're trying to reach. And let's say R3 chose the label of 321. And let's say that R4 chose the label of 427. And R5, because he is directly connected to that network, he would be advertising the reserved label of 3, or the implicit null, which is going to tell R4, hey buddy, go ahead and pop off that label. I'm the final destination. Now, as this idea sinks in that we're actually going to do two labels, the top label just to go across our service provider network, and the bottom label so that R5 can go ahead and forward it directly on to the customer, while that idea sinks in, let me tell you a couple reasons why this is so dang cool. Let's start off with R3 as an example. It's an example of a core provider router. R3 does not have to know anything at all about network 192.168.111.2. It doesn't know about it. It doesn't care about it. All it has to do is be part of a label switching path between R1 and R5. So it only needs to know about the networks that are internal to the service provider and not maybe the thousands or tens of thousands of routes that our customer edge routers may be working with, and that simplifies the routing and the processing required on these core routers. Because if we look at the routing table on R3, it's going to know how to get to R1, R2, R4, and R5, as well as the loopbacks that may be advertised as part of OSPF, but that's it. R3 and R2 and R4 don't need to know anything about the external networks, and that's because as they forward the packet from R1 to R5, all they're dealing with is that top label. For example, the packet as it's being sent up to R2 would have a top label of 209, and it would have the VPN label of 535. And what R2 is going to do is going to swap out the top label with the label that R3 needs and leave that bottom label intact. In fact, it doesn't even look at that bottom label. So on its way to R3 right here, the top label would be 321 and the bottom label would still be 535. Again, that bottom label, the VPN label, only has meaning or significance on R5. And then right here, between R3 and R4, R3 would swap that top label it would put on label 427 as the top label. It would leave the bottom VPN label of 535 in place. And then once R4 gets it, R4 says, oh my goodness, R5 is advertising the implicit null. And so what R4 will do, it'll do the PHP. But it's not going to tear off all the labels. It's just going to pop off the top label. So the packet that's being sent to R5 is going to have one label on it, 535. That's the VPN label that R5 needs to work with. And then R5 looks at that label and says, oh my goodness, an inbound label of 535. I know exactly where that goes. And then he can make the forwarding decision out interface FA2/0 to Acme Site 2. And of course, on that leg of the journey, there would be no labels whatsoever. It's just a naked IPv4 packet being forwarded from the provider edge out to the site. And then if Acme Site 2 has internal routing to do to reach that final destination, the customer would be responsible in their own organization for routing that packet correctly. Another really cool feature about having this label switch path where our core routers only care about that top transit label is that we could tunnel all kinds of stuff across this IPv4 network because the core routers aren't looking any deeper than the top label. So for example, if this customer over here wanted to run IP version 6 and they wanted IPv6 connectivity from site to site, we could actually pull that off by effectively hiding the IPv6 traffic as it's tunneled over the label switch path across the core network. Now our edge routers for sure are going to have to be speaking IPv6, but the actual core of our network doesn't have to know anything about IPv6 because all they care about is label switching between two IP addresses that they see as reachable. And that's R1's address and R5's address. So if we were troubleshooting this, we would grab, for example, one IPv4 route, if that's what we were troubleshooting. So we'd start by saying, is the packet being forwarded from the customer edge router to the provider edge? And that's really important. If Acme 1, for example, never learned the control plane, never learned that it should forward a packet in that direction to reach that destination network, that would be a problem. And then we could go back and say, okay, the control plane's broken. If a transit packet is sent and received by R1, it's going to come in on the interface associated with that VRF. Now, after R1 has received that packet, it's going to take a look, and in Ceph, it's going to say, hey, buddy, there's a VPN label, it's 535, and there's a transit label of 209 that you need to impose, and then go ahead and send that packet off to R2. So all that thinking and deciding of what should I do has been done beforehand. And that was all done as the control plane was being built. Now when the packet comes in, it's just time to execute. So it gets label switched across the LSP on its way to 5555, which is the next hop for that network. So if you'll notice, the top label gets swapped every hop of the way. And then R4, the router before the end of the LSP to 5555, pops off the very top label and just leaves the bottom VPN label of 535. And that's the label switching across the P routers. And then when R5 receives it, he has that VPN label that's left of 535, says, oh, I know exactly what to do with this, and it can go ahead and forward that packet out to the Acme Site 2 router. And that is the data plane that we're going to follow when using MPLS Layer 3 VPNs. Now, what'll be fun is this. Because we've already built this network from the preceding videos that we've gone through together, what we can do now is walk through a verification of the control plane. And again, we'll just pick one specific route that we can follow. And then we'll verify that it's actually working by sending some data from Site 1 all the way over to Site 2 for Acme as an example, just to verify that we do have end-to-end connectivity from one site of Acme all the way to the other. So here's what I'd like you to do. I would like you to write down our target network. You can do it in Notepad or you can do it manually on a piece of paper, but we're going to make this network right here on Acme 2. Let's do a show IP interface brief just to confirm what we're looking at. Yeah, this guy right here. That's the loopback address. It's being advertised as a 32-bit route from RIP, making it all the way down into multi-protocol BGP because of R5 doing that export out of the VRF into BGP, and that's the network we're going to verify all the way across. So let's go to the PE, and we could actually do a lot of baby steps as well. That's perfectly fine if we're troubleshooting. Let's just verify that we have VPN v4 routes set up for that specific network. And to see that, we'll do a show BGP VPN v4 for VRF 101:Acme and ask for the label information. Now again, our focus route is right here, just that guy. And this says that the local label for that network is 535. So his local label is 535. So if somebody sent this router a labeled packet of 535 it would have already calculated before that packet ever showed up what it's supposed to do with it. It's going to forward it to the next hop of 192.168.202.2, which is the IP address of our Acme Site 2 router. And there will not be any outbound label associated with that. And that's because we're not doing any type of LSPs between our customer and the provider edge in our topology. And that's normal when talking to a customer edge. Now, as we get into more advanced architectures, where we have provider to provider and we want to propagate labels, we might have some LSPs. But to customers, it's just basic IPv4 connectivity. If we want to look at more details regarding that 192.168.111.2, we can go ahead and say, please show me the VPN v4 information for that route. So right here is our route distinguisher for that route. There's the actual prefix itself. Down here in the extended community values, we have the route target of 5555:101. And here's our label information. There's our local label associated with that network. Now, if we wanted to verify, okay, what would you do if you did receive that packet? Who are you going to forward it to? We can do a show MPLS forwarding table for VRF 101:Acme with that specific address, and it will tell us what it will do. It says regarding that network of 192.168.111.2, it is a VPN v4 route. There's my local VPN label associated with that network. And if I had to forward it, I would go ahead and use FA2/0. And the next hop would be that IP address of Acme at Site 2. Now, to confirm that, we could also ask the router to show us the Ceph table regarding 192.168.111.2 for that VRF, and that confirms the same information as well. So our egress interface is FA2/0. The next hop is 192.168.202.2, which is Acme at Site 2. So from R5's perspective, he knows what to do. If he gets an MPLS labeled packet that says label 535, he knows exactly how to forward that. He's going to strip all the MPLS stuff off, forward it without a label to this next hop. Now, the next question is that label of 535, that VPN label, and the route to 192.168.111.2, did that really get advertised over to R1 via multi-protocol BGP as a VPN v4 route? So what we can do here on R1 is simply ask to see the VPN v4 routes for the VRF called 101:Acme and to see the label information about those routes. And again, here's our focus route right here, the 192.168.111.2. Right here it says the next hop is 5555. We learned this via iBGP. So the next hop is R5's address. And look at this, we do have an outbound label associated with that route, and it's 535. So regarding this VPN v4 route that we're looking at, when we send a packet, a transit packet, towards that IP destination, we're going to impose that bottom VPN label of 535. Now, R1 is saying this is complete faith. I don't know anything about label 535 except for the fact that it was advertised as part of the BGP routing information for that VPN v4 route. So somebody, in this case R5, cares about that label, and as a courtesy, R1 will impose that label as the bottom label. It will also set the bottom of stack bit to a 1 to indicate that it really is the bottom label. Now check out this IP address for the next hop. It's 5.5.5.5. Now we absolutely have an MPLS label switching path to get to 5.5.5.5. And whatever the top transit label is to reach 5.5.5.5, that's going to be our top label. So on the bottom we'll have 535 for the benefit of R5, and then our top label will be the one that we're going to use to reach 5555, which, as we now know, is the label that R2 has advertised to us regarding reaching 5.5.5.5. And if we wanted to see the details regarding MPLS forwarding for 5.5.5.5, we simply ask the router for that information. So regarding the next hop of 5555, our local label is 106. So if somebody handed us a labeled packet of 106, we would say, great, I'm going to swap it out with label 209, forward it out gig 1/0, and the next hop is 10.14.0.2. So as we send the packet, the top label, the transit label would be 209 as R1 sends this packet on its way, and the VPN label would be 535. Now, all of the decision-making process has already been done. Ceph is populated, it knows the labels, it knows the next hops, it knows everything it needs to do. And if we wanted to ask the router, hey, please show us the Ceph information regarding 192.168.111.2 for VRF 101:Acme, it would tell us. So regarding this network, it would go ahead and send it out gigabit 1/0, the top label, also called the transit label, would be 209, and the VPN label, the bottom label, would be 535. It's telling us right there exactly what it's going to do. And then when R2 gets that top label of 209, it'll simply swap the top label with the label that R3 has advertised regarding 5.5.5.5, and it will simply be label switched in the direction towards R5. Now, when R4 does finally receive the top label and the bottom label, it knows that the next hop of 5555, it needs to pop off the top label, so it will do that. It'll do the penultimate hop popping and forward the MPLS packet with just that bottom VPN label of 535, at which point router 5 gets it and says, I know what to do. This is my local label of 535. I need to forward this packet out to Acme at Site 2. So to test this, what I would like to do is let's go up to Acme Site 2, and I want to enable Telnet on that device. Now, generally using Telnet in a production network is a really bad idea because all the text is sent in the clear. I suppose if you put it inside of some type of VPN that could protect it. But in our case, I want to enable Telnet and make it really easy to Telnet to Acme Site 2, just so that we can verify our connectivity over the label switching path and through the MPLS network to get to that destination. So all I've done is gone to VTY 0 through 4. I said no login is required, and if anybody does connect, hey, just give them privilege level 15. No need for any login. Next, what I like to do, let's go over to Acme at Site 1. So at the moment we're at Acme Site 2, top right corner of our topology. Let's make a road trip over to Acme Site 1. And what I'd like to do with you is let's just verify that we have a route to 192.168.111.2 in the routing table. That'll just confirm that the control plane is working. And there is our route, 192.168.111.2, learn via OSPF. Our next hop is 172.16.101.1, which is R1's IP address on the interface that connects up to customer Acme at Site 1. So that part looks great. We have a route. Next, let's verify that we have reachability and have a little fun at the same time. We're going to do a trace route, and on an iOS router, if you don't disable TTL propagation, we can see the entire path and all of the labels in the path from Acme Site 1 all the way to Acme Site 2. Now, as a service provider, if we did not want our customers to know our labels that we're using, we can turn off that feature and basically hide the core of our network so they wouldn't have any knowledge of it by disabling TTL propagation. But by default, it's on, which is really handy for learning. So the first hop was the PE interface. The next hop was R2, and as we sent it to R2, we imposed a top label of 209 with the bottom label, the VPN label of 535. When R2 got that, it swapped off the top label and put 321 there, left the bottom VPN label there, and forwarded it on to R3. When R3 got it, it swapped off the top label of 321, put a new label of 427, left the bottom label of 535, and sent it on to R4. Now when R4 got it, it realized that, hey, I'm being advertised the implicit null from R5 regarding 5.5.5.5. So I'm going to be a good buddy. I'm going to do that PHP game, the penultimate hop popping. I'm going to pop off the top label as a courtesy and then simply forward the bottom label that's still there onto R5. So R5 actually receives this VPN label of 535. It says immediately, I know what to do with this. And it forwards it up to Acme Site 2. And that's the last leg of our journey with no labels whatsoever. So there was no labels from the customer for the transit traffic coming in, and there's no labels on the final leg of our journey as it goes up to the customer at Site 2. So since we can trace route that address, we should also be able to go ahead and telnet to it. Now, as we telnet, if we're going to the right site, if we have our VPN set up correctly, we should be telnetting to Acme at Site 2. And that's what's happening right here. So my console's sitting at Acme Site 1. However, I have telnetted from Acme Site 1 over to Acme Site 2 over this path, which includes the LSP going over the core of our network. Now, one of the other amazing features of an MPLS Layer 3 VPN is this. If we add routes at either side of our customers, those routes can dynamically be advertised into the PEs, who can dynamically create labels, put them into multi-protocol BGP, and advertise those routes out the far side to the other sites. For example, we're sitting at Acme Site 2. Let's go ahead and simply create a loopback interface. We'll create loopback 8. We'll give it the IP address of 8.8.8.8 with a 32-bit mask. And what I also want to do is I just want to confirm that that really did get into the routing protocol. So we're running RIP over at Acme Site 2. And the network statement said everything comes in. So I just wanted to verify that indeed loopback 8 that we just created is in RIP. So from the control plane perspective, R5 has got that route, or within 30 seconds or so it should, based on triggered updates happening or not with RIP. And then R5 will redistribute that into multi-protocol BGP, which is an export, which will be advertised to R1, who can then do the import, and then have that route advertised back up to Acme. And that should all happen dynamically. So let's do this. I'm going to type in exit, and that'll exit our telnet session that was currently going to Acme Site 2. And now at Acme Site 1, and I'll scroll up for this. Initially, we did a show IP route, and we simply had two OSPF learned routes, a 192.168.111 and a 192.168.202. Now if we do an up arrow key a few times and do a show IP route OSPF, check this out. There's our 8.8.8 network right there. And the reason we know it as an IGP OSPF learned route is because of the control plane that we're using in the MPLS Layer 3 VPN. And we should be able to trace route to 8.8.8.8 and have it work, and it will also show us what the VPN label that R5 has assigned for that 8.8.8.8 network. So in this case, it chose to use 505 as the label it chose as the VPN label. And our transit labels haven't changed. And that's because the next hop from R1's perspective is still R5. So it's going to be label switched from R1 to 2 to 3 to 4 to 5. So that LSP is not going to change. So it's just the VPN label that's changed because it's a new network. And if we added 100 more networks, there would be 100 new VPN labels for each of those networks that are being learned by the provider edge from the customer. One last thing that I think would be a lot of fun to do is let's do a packet capture somewhere in the path here. In fact, let's do it between R2 and R3. We'll capture right there. And if we capture those packets, what we should expect to see is for transit traffic, we should see a label of 321. And if the packet's going to 8888, we should see a VPN label of 505. So let's do that right now. We'll bring over GNS3. We'll simply right click on the link between R2 and R3. We'll say start capturing. Click on OK. And I've got GNS3 configured to automatically start Wireshark. So there's whatever traffic is on the wire between R2 and R3 at the moment. And let's go ahead and do a ping. So I'm going to do a ping of 8.8.8.8 with a repeat count of 1. There we go. It was successful. And now we'll go back to our packet capture. So I'm going to go ahead and say stop there. I'm also going to go into GNS3 and tell GNS3 that I want to stop the capture as well. So if we click on View, and we go to Docs, and we have the Captures doc, you can right-click here and say Stop All Captures. Or you could right-click on this link again and say Stop Capturing. Either way, just as long as you turn it off so it doesn't eat up a whole bunch of disk space and CPU while you leave it running. So I'm going to minimize GNS3, and let's take a look at this capture. So what we're looking at is ICMP traffic. So we'll go ahead and just type in ICMP, press Enter. There we go. So there's our echo request and our echo reply. And if we take a look at the details, here's the layer 2 header information. So we sourced it from the MAC address of 2222, which I hard-coded on R2. And it's destined to the MAC address of R3, which I hard-coded with a whole bunch of 3s in it. And in the layer 2 header, check this out. Instead of saying, hey, the next protocol is IP, it's saying, hey, the next protocol is MPLS. That's hexadecimal 8847. So anybody decoding this packet would know what to expect next, including a label switch router or anything else that's processing and de-encapsulating these packets. So if we go one layer up to the MPLS header, we have our top header. So there's label 321. And I'll scoot this over just a little bit. And 321 is exactly what we expected. The MPLS bottom of label stack is not set, which implies, hey, there's another label below me. Don't give up. And then we have a TTL of 253. So what happens by default, the TTL on the IP packet as it begins the label switch path, that TTL gets carried over into the MPLS header. And then as that label is switched through the LSP, it's going to be decremented, that top label, every time it goes through a router. And then if we open up the bottom label, in this case this is the VPN label, there's the label of 505, which we expected to see based on this information right here. So there's 505. That looks great. And we have the bottom of label stack set to 1, which means, hey, I'm the last label in the stack. And then after that, we have the actual payload that was trying to be delivered, which is a packet sourced from 172.16.101.2, which is Acme's Ethernet interface, destined for 8.8.8.8. And inside, there's an ICMP echo request. Now, the reply packet coming back from 8888 going to 172.16.101.2, that may surprise you a little bit because we haven't looked at the details of those labels. But here's what we can expect if we open it up. R1 is going to have a VPN label associated with that address space. So that will be the bottom label. So it's going to start with 1 something. And the top label is going to be based on the LSP that's trying to get to 1.1.1.1. So the top label that R3 is going to impose as it forwards this packet from R3 to R2 is going to be the local label that R2 has allocated for 1.1.1.1. So we're expecting 2 something as the top transit label and 1 something as the VPN label. So if we open that up, so now we're looking at packet 17 here. The top label indeed is 206. That's the local label that R2 has allocated regarding the network 1.1.1.1, which is R1. And then the bottom label is 107. And if we looked at the VPN v4 routes regarding the destination network of 172.16.101, and I believe that was a /30 network, we would see that R1 has assigned 107 as the VPN label for that network. So when R2 receives this, it's going to say, oh my goodness, regarding 1.1.1.1, R1 is advertising to me the implicit null, which means I need to pop off the top label, says R2, before I forward this MPLS packet. It would leave just the 107 label that R1 would then receive, and then R1 would say, oh, label 107? Boom, I know exactly what to do with this. And it could forward up to Acme at Site 1. Or if this device is directly connected, it would go ahead and simply deliver it to that final destination. In this case, it is. That's the IP address of Acme 1's Ethernet interface that's connecting to R1. And what I'll do, I'll include this trace file as part of the Nugget Lab files for this video, so you can refer to it and look through it if you like. Your mission, should you choose to accept it, is to practice what we've done together in this video, including creating a brand new route on one of our CE devices and verify that it does show up on the corresponding CE on the other side. And then take advantage of the commands we used in this video to verify the details, such as what is the VPN label, what is the transit label. And as you focus on the control plane and the data plane, I would consider using one route at a time and focus on that one route for the entire path. I'd also love for you to take a look at the opt-out questions at the beginning of this video just to help reinforce the concepts that you've learned by watching the video and by doing your own hands-on practice. I have had a great time and I'm so glad you joined me for the video. I hope this has been informative for you and I'd like to thank you for viewing.